Okay, so here's the first of many recordings, starting with section 4.2, the mean or expected value and the standard deviation, for probability distributions in particular, which goes for all probability distributions. So this will go into the next section as well, and if you wanted to go on from there to look at the future sections, you could look at those as well and use this. So expected value, it's what we expect to come out in the end result. So after a long period of times where you play the game over and over and over again, if it is a game or if it's something else, you would expect this certain result. This long-term average that you would get is actually technically the mean, the probability, the population mean in a way. So large numbers. So if we use large numbers, so expected value is the long-term average or mean, and what you would expect after a long time of doing this over and over again. So, and we've talked about the law of large numbers in the past. So let me move on. So when evaluating long-term results of statistical experiments, we often want to know the average outcome. This is the long-term average, also known as the mean. So the mean, let's see if this works. All right. So let me do it this way. Sorry, getting used to this. So we're going to have little issues like this as we go through, right? So you just have to deal with it. You can fast forward as we go. And let me change the color here. So home color, so we know it's a different. That's the answer. So there we go. The mean or the expected value. So, right, let me bold it again. So there we go. Or the expected value of the experiment, which is denoted by the letter mu, right? So notice we are using mu and not x bar. Mu is the population mean in this way. And we are talking about population means and population standard deviations in this case. So for when we get to the standard deviation, we'll be using the population standard deviation formula. Excuse me. So to find the expected value, or the long-term average is what we can call it as well. Long-term average. Let me bold that, make it look good. So we are technically, what we're technically finding again is mu. So Control C, little Control V here, just to get mu in there. We'll bold that and make it blue as well. Simply multiplying each value of the random variable by its probability and adding their products. It's a pretty simple formula, but I wanted to use GeoGebra to kind of get you used to GeoGebra, to see GeoGebra as well. So I'm going to go over GeoGebra's results and try and get you used to it. But no, this is an easy formula that you can do by yourself within any calculator as well. So all right, so let's talk about an example. So example 1. A men's soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2, 20%. The probability that they play 1 day is 50%, or 0.5. The probability that they play 2 days is 30%, or 0.3. Find the long-term average or expected value mu of the number of days per week the men's soccer team plays soccer. So to do the problem, the first random variable is x. So we need to know what this means, right? And we talked about probability distributions last time, right? In terms of, right, we have to have a certain outcome. So these are the days of the week, the number of days of the week that the soccer team actually plays. And we can only have 0, 1, or 2 for this particular soccer team because at most they're going to meet 2 times a week. So I'm not going to have any one past that. So I'm not going to put down here in my probability distribution that I have 3, 4, 5, or 6, or 7 in this case. But we could for different probability distributions. So here are my possible outcomes, right? Again, the number of days per week the soccerman teams play soccer that week. So And this is the probability that we are given up above. So we could fill out this table, but it's already filled out for us. And what we really want to do is just to find the expected value. So I want to find the expected value. So let me enter. No, that's not working. Let's enter it down here. So expected value, also known as mu. Where was that? I think I still have it copied. So also known as mu is equal to, and we have a formula listed below, but we will literally just take the zeros times the outcomes times the probability of that outcome, right? So I would take 0 times 0.2, 1 times 0.5, 2 times 0.3, and add all those results together to get the expected value. Just to show you, GeoGebra can do it, and we can play through it in GeoGebra. So let's do that, and we'll see what we get. So let me first go ahead and do what I'm doing with all my answers. No, that's not good. That's not good. Stop. I didn't realize I selected all of them. Here we go. Oh, it was already bolded. Beautiful. All right, and then we'll enter the answer right there, rounded a certain decimal maybe. So I want to use GeoGebra for this. So what I'm going to do in GeoGebra to make it easier on myself, if I want to calculate multiple things, right? Maybe I want to calculate the mean and the standard deviation for one. And it doesn't make too much sense to be doing it on this 3 outcome table probability distribution. But let's use it to explain it in this case, and we'll use it on the next one too. So the first thing I'm going to do is I'm going to make up a set. Right, and we talked about this, so I'm going to enter A equals, and I got my squiggly brackets, and I'm going to enter my set of outcomes. So here are my set of outcomes. I got 0, comma 1, or comma 2. Those are my outcomes. Those are my days a week my soccer team can meet. But in this case, I also need the probabilities, and the probabilities that are given to me, I'm going to enter in a different set. So I'm going to enter, call it B, capital B. I like capitals because GeoGebra uses lowercase and stuff like that, so I'm going to use capitals to make sure I differentiate between what GeoGebra does. And I'm just going to enter the probabilities in order. If I mess up the order, it's not going to know which one goes with what. So in this case, since I have them in order, it understands that 0 goes with 0.2 and 1 goes with 0.5 and 2 goes with 0.3. So with that in mind, that's all I really need are my sets, and now I need to find the expected value, or mu. Since I'm looking for a mu, an expected value, then I'm really looking for what's called a mean. A mean of the data. So a mean of the data, I could use this, not really, but this is really what I want. So, and really it's the same formula, but GeoGebra understands that when you put a comma between 2 sets, it then differentiates in that this is your list of numbers and this is the list of frequencies. And that's all this is, right? This is our outcomes. These are my list of numbers, and this is the frequency, or technically the relative frequency of getting that outcome, but it works whether you have a frequency or a relative frequency. So let's go ahead and use mean, and I'm just going to type it in, mean, and I'm going to use A as my first set, comma. Notice I typed in the mean for that first set, but as soon as I enter capital B in there, it finds the expected value for me, which is 0.1. So let's 1.1, not 0.1. Come on, Andre. So 1.1 is the expected value. So coming back over here, I have the expected value. Okay, with that in mind, we found the expected value. So what that means is that in the long run, we would expect this team to meet 1.1 days out of the week. Out of the week. So in the long run, we would expect this team to meet 1.1 days out of the week. So there's an explanation of what the expected value is. And so this 1.1 is technically in terms of days per week. All right. So that's that. Let's move on to example should be 2. Don't know why it's 1. 2. I changed it. So, all right. So moving on to the next one. So find the expected value of a number of newborn babies crying wakes, the number of times a newborn baby's crying wakes its mother after midnight. The expected value is the expected number of times per week a newborn baby's crying wakes its mother after midnight. Calculate the standard deviation of the variable as well. So we're going to calculate both the expected number, the expected value, and the standard deviation. So we got expected number and the standard deviation in this case. So we'll talk about both. So, okay. So I want to do this, and so I'm looking at the data, and I'm thinking, okay, well, here's my data, right? It doesn't fully make sense. We've gone over this problem in class as well before this whole issue came up with the coronavirus. But, right, these means the number of days, the number of times the mother is woken up after midnight by a crying baby. So we have 1 time, and it's per week, so 0 times per week, 1 time per week, 2 times per week, 3 times, 4 times, 5 times per week. So, right, which I believe is totally unrealistic for how many times a mother is woken up by a newborn baby. So, and here are the probabilities. So one thing about this probability distribution that I really don't like is it's labeling it here. It's just showing you the notation, but this notation is technically not a good way to write that. So I'm going to go ahead and delete that in front of you so you can see me saying, okay, this is really just the probability. So it's just trying to show you and explain different notations as we go. So first thing I want to do is I want to calculate the expected value. So let's go ahead. This time I'm going to insert a text box. See if I can use the text box. Maybe not. So where are my text box? Text, insert, text box. I don't know what that is. Okay, anyways. So let's just do it down here. So first thing I want to do is find the expected value. Let's use this notation I had up here, Control C. And we'll come back down here, Control V, so that way I can type it in and you don't have to see my horrible writing. All right, so same thing here, right? I'm going to use all these numbers and do the same thing to calculate the expected value. It's a new problem, so with Geogebra, we always want to try and go fresh from the beginning, so that way we don't have any issues with labeling our sets. But here I go. I'm going to create 2 sets. A equals the set of numbers of times the baby wakes up the mother per week. 0, 1, 2, 0, 1. I'm putting a space. Why am I keep putting a space? I don't know. 2, 3, 4, or 5 are all my expected values in this case. Next, I'm going to put in the probabilities. So a B equals the set of 2 divided by 50. Let me just try that. Comma. Oh, I'm looking at the comma. Comma's in the denominator. I don't want that. So let me use the arrow key. Scooch over, and then I'll enter the next one. 11 divided by 50. Scooch over. Comma. 23 divided by 50. Scooch over. Comma. 9 divided by 50. Scooch over. Comma. 4 divided by 50. Scooch over. Comma. Yeah, this is totally lame. 1 divided by 50. And there's all my set of my probabilities. And, right, Geogebra knows to order these. Oh, look at that. It kind of simplified it. That's pretty cool. Sorry. Geeking out about Geogebra right now. So, right, it knows to order these in the sense that this 0 goes with 2 over 50, 1 goes with 11 over 50, and so forth and so on. And it might even use those things. Oh, look, I could approximate those. Sorry, geeking out. Stop, Andre, stop. Get to the point. Okay, so with that in mind, we can then calculate the mean as we did before. So I want the mean, use parentheses, A, comma, capital B. And there is my expected value. We would expect the mother to be woken up 2.1 times per week per week by the child, by the baby. Let's use baby. So now I want to calculate the standard deviation. So let's talk about it. Standard deviation, StDev, right? Standard deviation in this case, we are talking about, right? We did use a mu in this case, although we're talking about the mean, which really has no effect on whether you're talking about a population mean or sample mean. So we calculate it in the same way. But with standard deviation, we understand that there's a different formula, whether you're talking about a sample or a population. With that in mind, we want to make sure we understand that since this is a probability distribution, this essentially lists out all the possibilities and their probabilities here. So we are assuming that this is a population data in a sense. So we are going to use StDevp, right, which is equal to the population standard deviation. Deviation, and I can't spell deviation, but luckily I'm on Word here. I can't spell population either. Oh my gosh. Woo! This is going live online. All right, population and deviation. There we go. So we're going to use that StDevp formula in order to calculate this. So let's go for it. Let's see what happens. So StDevp, boom, look at what I got. I got a choice of a list of raw data. I don't have data, I don't have that, right? But I have a choice of a list of numbers and list of frequencies. In this case, technically, relative frequencies. But it can do it with relative or regular frequencies. It understands how to do that. So let me use that, and I'm going to enter A, right, comma, B. Bam! There is my standard deviation. Let's go ahead and round it. Let's say I wanted to round it to 4 decimal places. That would be 1.024. That's 3. I need one more. Am I going to put a 6 or am I going to put a 7? Oh, the 9's after the 6, so I'm going to make it a 7. Since it's 5 or more, we let it score. So we are talking about 1.0247 times per week are the units on this that are woken up by the baby. So here is my answer for my standard deviation, and I am just going to go ahead and make this blue. Let's bold it, let's italicize it so it looks like the one right above that. All right, so hopefully there's no questions about that. So moving on, I'm going to talk now about the mean. The mu of a discrete probability function, right? In other words, right, a probability function, so which we call PDF sometimes. A PDF is a probability discrete function, distribution function, actually, not discrete, but we are talking about discrete numbers in general. And next chapter we'll be talking about continuous values. So with that in mind, right, we're given the formula here. So this is the technical formula for what we were talking about before. So this technical formula, just to go through it, right, I can actually go to Excel here, and I have essentially my data that we listed up in the previous one. So what it's saying is essentially I can multiply x by p of x for all these values. So I can multiply x times p of x. I don't know why I would want Excel actually. Let me go back and let me say I just want to show you that we get the same mean out if I use this formula, if I use Geogebra. So if I use that formula, what I can do is I can say, okay, well, so I would take each value, I would take 0, and I would multiply by, right, I would multiply by the probability of 0, not add, multiply, which would be 2 divided by 50. And then I would scoot over, I would add, then because, right, this large sigma means addition of all of these things for each x. So for each x, so the next one would be 1, and I would multiply it by 11 divided by 50. I scoot over, add it to 2 times 23 out of 50. Scooch over, right? So that's this one, 2 times 23 over 50, plus 3 times 9 out of 50. Scooch over. Plus 4 times, what is that? 4 out of 50. Scooch over. Plus 5 times, last one, 1 out of 50. Let's see what happens. Is it going to work? Is it going to work? Is it going to work? Oh, wait, what is that? Why is it giving me a fraction? I don't know. Let me hit enter and see what happens. Oh, enter. Oh, maybe I don't want a fraction. Maybe I do. If I want the fraction, that's okay. I can work that. Let me just show you the formulas out there. There's the formula, right? And here's the fraction, but I can approximate that fraction by hitting this button, or I can go back to the fraction. Oh, I love Geogebra. All right. So anyway, so moving on to the next one. Just wanted to show you that this formula works, and that's how we work this formula. All right. So the next thing is calculating the standard deviation. And here is the beautiful, beautiful formula for standard deviation. Yes, we can use that formula for standard deviation. Do we want to? God, no. So let's move on from that. I'm not going to show you that it works. It does work. You can try it yourself, right? So we're going to use Geogebra when we're talking about standard deviations, because typically we don't necessarily have just 5 things or 6 things of data, right? Here we have, maybe we have lots and lots of data. So, but that is the formula, just to scare you a little bit. So when all the outcomes in the probability distribution are equally likely, these formulas coincide with the mean and standard deviation of the set of possible outcomes. Okay. Anywho, so let's move on to another example. Here's example 3. So we have a game of chance, a real world kind of idea of where expected value or expected profit, in this case, can come into play. And essentially in the lottery system. In the lottery system, it also comes into play in the into insurance industries, life insurance, so kind of things, and other things like that. So we might have examples of that on your homework. So let's calculate the probability or the expected value of playing this game in the long run. So we suppose we play a game of chance with 5 numbers that are chosen from 0 through 9. A computer randomly selects 5 numbers from 0 to 9 with replacement. You pay $2 to play and could profit $100,000 if you match all 5 numbers in order. You get your $2 back plus $100,000. Over the long term, what is your expected profit of playing the game? So to let you know, right, we could fill out this table ourselves. I don't know why it gives it to us. We should have filled this out ourselves. But nonetheless, when we have a loss, right, when we don't win, we lose that $2. But when we profit, it says we're going to get back our $2. We get back our $2, whoop-de-doo, on tops of the $100,000 that they're going to give us, plus the $100,000. So we don't get $102. Do you understand that? Because you're just getting back that $2 you put for your ticket, essentially, to play this game. So you are just winning $100,000 or losing $2 if you just buy one ticket. So, okay. So the probability of winning or losing. So the probability of winning or losing are actually given to us down here. So let's kind of go over this and just make sure we understand what this is saying for us. So the expected value, so if we want x, the x is the amount of money you profit. So here is my x. This is the amount of money we profit. In this case, we actually lose money or gain money. And the values of x are not just 0 through 9, since this is just exactly the numbers that we use to play the game. But our actual outcomes are that we lose $2 or we gain $100,000. So those are the values of x. So the values of x again are either -2, or 100,000. So let me bold that, blue, bold, right? Maybe I should do some underlines for these. Bam. All right. To win, you must get all 5 numbers correct in order. The probability of choosing one correct number is blank. So the probability of choosing one correct number is what? So is 1 out of 10. 1 out of 10. Sorry, I had to think about it for a second. I was just talking without turning my brain on. So there we go. I got my brain on, so don't worry too much. All right, so there's my answer for the probability of choosing one correct number is 1 out of 10. You may choose a number more than once. Yes, we may. So what that means is we're doing with replacement. So, haha, I'm reverting back to chapter 3. Since it's independent with replacement, it means that we are going to multiply this 5 times, or we're going to take 1 over 10 to the 5th power, which the probability then of getting all of those correct, which is what it would take to win this, would be 0.00001. So that is the probability of winning. 1, 2, 3, 4 zeros after the decimal, and 1. Which then tells us what the probability of loss is, because we have that complement idea. We have that complement idea of taking this probability be 1 minus 0.00001, which would equal 0.999999. Yes, there it is. So this would be the probability. But what we really want is just that. I don't want to list out what I did to get there, so let's just leave it like that. But I'm using that complement space, right? I add these up and I get, 1, which is one of the definitions of a probability distribution. All right, so with that in mind, now that I have my probability distribution labeled out, right, I can use that to find the expected value. So let me go to Geogebra again and let me say, I want to enter this. So let me go to new because there's way too much stuff there. So let's don't save. And let's just cancel out what we have and start anew, right? So the expected value of this thing would be just I take -2 times this and I take 100,000 times that. So, and I add those together. So I'm just going to do that, or I can use the mean. So let's just do the multiplication. So -2 times 0.99959 plus 100,000. I need 5 zeros for 100,000 times 0.4 zeros and a 1. And then we get our expected value. So our expected value, all right, our expected value, I'm going to go back and steal this stuff again. Control C. Our expected value of this probability distribution, this game we are playing, is that we would expect in the long run, if we played this over and over and over and over again for like 1,000,000 days straight, we would expect to lose so that's a negative 0.99998 dollars on average. So what is that? What is that? That's really we would expect. So we would expect to lose $1 per game or per ticket, really. Okay. So basically lose $1 on tickets. So we would lose that dollar and it'd be gone, right? And if we play that many times, 1,000,000 times, yes, we are losing $1 million, right? So this is how how they actually make money in the lottery system, is that there are many people playing this game. Even though they may be giving out $1 million, they have 2 million people playing this game, and so they're making $1 million on top of what they get back in and give out. I mean, so okay. So with that in mind, let's move on. So our last example actually. So suppose you play a game with a biased coin. You play each game by tossing the coin once. The probability of heads equals 2/3, and the probability of tails equals 1/3. If you toss a head, you pay $6. If you toss a tail, you win $10. If you play this game many times, you will come out ahead. No, no pun intended. Or maybe it was. I don't know. I don't know the author. Well, I do know the author, but I haven't talked to her about this problem. So, all right, define the random variable x. So define the random variable x. X is what we're talking about. X is equal to, what is it? I don't know. So you play each game by tossing the coin once. The probability of heads is this. The probability of tails is this. If you toss a head, you pay $6. If you toss a tail, you win $10. So I am winning money. I am losing money. So if we win, we gain $10. If we lose $6, right? If you toss a head, you pay $6. So my x, right, is defined as, so x, my random variable, is defined to be the amount of money won or lost. In this case, x is equal to, x has the possibilities of being equal to any of these, right, possibilities. I could win $10, or I could lose $6. Oops, lose $6. So negative $6. So this is my random variable. So let me bold that and make it blue. Bam, bam. Yeah, that's good. There we go. Oh, I was doing italicized too. There we go. So that answers that question. The other question asked for me to complete the table, so we could also lose $6. So we win or we lose, right? And I'm going to put the negative there because Geogebra and any calculator would need the negative and need to understand that this is a loss in some way, shape, or form. So, and if I had 1/3 of a chance of getting a heads or winning, then that means I have blank thirds. Yes, you are right. Good job. 2/3 of a chance of losing. More of a chance of losing. I hate those games. So I like winning all the time. So there we go. I forgot to italicize. Those are my answers. So we filled out the table, right? How did I get that 2/3? Because these two should add up to 1. And also it tells me up here. So I might have cheated a little bit, but I didn't say that. Okay. So what is the expected value mu? Do you come out ahead? All right. So I want to calculate the expected value mu. Now that I have this probability distribution labeled out for me, let me go over to Geogebra and I'm going to calculate it one more time with the mean. So, and I'm just not even going to use sets for the mean. So let me just use the mean, and I want to separate my two x's. So I'm going to put in the sets in here. So I'm going to use a little, right, set notation. So I'm going to use 10, comma, -6. I'm going to scooch over, use a comma there to separate my other set, which would be 1/3. Scooch over, comma, 2/3. Oops. Nope. Something happened. 1/3. Okay, I'll fix that. Don't worry. Delete. There we go. Comma. And then 2 divided by 3. Enter. And there is my expected value. So mu, Control C. Again, I'll just put it right here. The expected value. We would expect to lose. Essentially So I'm going to put a negative dollars. I'm just trying to get the formatting right here. 0.67. If I round to 2 decimal places like it's cents, right? I expect to lose basically 67 cents every time I play this. This is in the long run, though. I could win sometimes, I could lose sometimes, but in the long run, if I play this game over and over again a million times, I would expect to lose 67 cents every single time. So I should expect that in the long run, I would lose negative 0.67 cents per game, per flip. Let's say per flip of the coin. So hopefully you understand that, right? This idea is not one that we necessarily use as an individual playing this game, but this idea is one that the casinos would definitely use in order to understand that if they were to do this game and have this, they would lose, right, this much money every single time they play. It's not a good example, right? We don't want that as a business. We would want to gain money, and even the cents on the dollars, right? This is what they do, just little amounts of money that they make, but they got so many people coming in those things, so much money coming into that thing that they make bank. Just look at those buildings in Vegas and you know they make bank, and it's off of you. So that's my little lesson for you today. Don't gamble. Enjoy it. All right. Have fun.